Here you are.
Thank you.
You're welcome. Have a nice day.
Hey, you do the same.
Thanks. Oh, and be careful at the door. It can be a little tough to open.
This thing is broken. You guys really need to get it fixed.
I don't think it's the door.
Well, it has to be. It was the only thing I was pushing on.
I know. I still don't think it's the door.
I'll bet you it is.
Okay, if it's the door, then your next drink is on me.
You're on.
Well, how are you going to figure out if it's the door?
I don't know. I think I need a scientist.
It's iodine, guanine, cytosine, and thymine. Science you find in the city. Energy's discrete on the corner, on the street. It's science you find in the city. It's oscillators, regulators, emulators, generators. Science you find in the city. It's time to explore what science is for. Out the window and beyond the door.
City Science with Mike Davis.
Hello, Professor Mike.
Hey, hi, how are you?
Hi. What are you doing there?
I'm just having some fun, you know, some scientist downtime.
Well, what do scientists do for fun in their downtime?
Well, I like to take little candy bars, toss them in liquid nitrogen, freeze them, and then smash them up.
Working something out there?
Nothing out of the ordinary. Why? Why do you ask? Candy? Okay, there's more for later. What's up?
Well, I was getting some coffee the other day,
Yeah.
and when I tried to leave, the door is really hard to push. So I told them that there was a problem with the door, and the coffee girl didn't agree with me.
Yeah.
So we made a little bet.
And you bet that the door was not opening easily because it was defective.
Yeah, can you help me with that?
I think I can help you, but I'm pretty sure I can tell you it's not the door.
Really? That sucks.
No, it pushes. That's what I'm going to show you. You know what you have is a gas problem.
That's not a very nice thing to say to someone.
I mean gas like the phase of matter, not gas like you just had tacos or something.
Oh, I see. It's a gas.
Yeah, but that's the hard part, because you can't see gases. And it's easy to pretend like they're not around you, but you can actually see and feel the effects of gases pretty easily.
Are you going to show how?
Oh, absolutely. But first, let's see if you can describe a gas.
You mean me?
Yeah, you and some other people. How would you describe a gas?
Okay, let's ask some people about gases and see if people know what they are. Do you know what a gas is?
Gas, like petroleum gases.
Gas can be clear like this, or it can be foamy. Usually odorless and clear.
It smells. I have a baby that's full of gas. Does that count?
Yeah. Keep that lid covered.
Takes up space, but can be invisible.
It's not a liquid.
It's in vapor form.
Give me an example of a gas.
Helium.
There's like neon and other gases out in the universe.
Very good.
Yeah?
Yes, a gas is a phase of matter where individual particles, either atoms or molecules, are completely separate from one another. They're bouncing all over the place, off each other and the walls of the container. When a gas is inside a container, it takes up the entire container, no matter what the size or shape of it is.
So, no matter what the shape or volume a container is, the gas will completely fill it up.
Yes.
But what about a liquid? Don't they work the same way?
What do you mean?
Well, this blue liquid is in this skinny container. If I put it in this container, won't it stay the same shape?
Yes, but do you think it'll take up a new volume?
No, I guess not.
And that's what's special about gases. Gases would fill both the shape and the volume. This liquid just adopts the shape. Down here there's the liquid. The rest of it is filled with gas.
Oh, that makes sense. Volume and shape.
Right. So we're going to focus on three different things: pressure, temperature, and volume. This is a red balloon. Do you know how we fill up balloons? With air, again, which is a gas. All I'm going to do, is we blow into these and fill up a nice red balloon. Really simple. This is something very cold. This is called liquid nitrogen. This is colder than you've ever been on the coldest day of your life. It's 196 degrees below zero, so I'm going to pour some of this in here. It is so cold. It's so cold. All right, so I've got some liquid nitrogen sitting in here. A little more. And what I'm going to do is just stick my balloon in here.
Is that freezing your hands?
It's not freezing my hands. My hand's nowhere near the nitrogen. So I put a balloon in here. Do you guys remember the color of the balloon?
Yeah.
It was red. Was it purple?
Oh my God, it changed the color.
Did it change the color?
Perfect.
Or maybe it's still in there. Look what's happening to this balloon.
It's getting serious frost.
Is it getting bigger or smaller?
Bigger.
It is getting bigger. And I've got the red one right here too. They were both in there. This balloon, we blow it up, you know, we use our breath to blow it up, it gets nice and big. It's full of a gas. But inside here, it's really, really, really cold. So when I put this in here, that gas doesn't take up as much space as it used to take up. It wants to take up less space. That's called Charles' law of gases. So I've got it in here now, and it's getting cold. And now it's warming up, and you can see it's taking up more and more space. And eventually, it's going to take up as much space as it once did before. Again, Charles' law of gases. When things get really, really cold, they want to take up less space, so they really, really shrivel up. Okay?
That is pretty cool.
Yes, and there's a name for that.
What is that called?
That's Charles' law of gases, and it states that the volume and temperature of a gas are directly proportional at constant pressure. Easy, right?
Not exactly.
All right, well, think of it this way. Temperature and volume are two guys on a swing, and they go up and down together.
Well, that I get.
Good, so let's move on to something else, like pressure.
Pressure, like a push?
Yes, but in the sciences, we refer to pressure as a force divided by an area. And that force comes from moving molecules.
Well, that pressure must be pretty small, right? I mean, if gas is made up of molecules and atoms, well, they can't weigh very much, can they?
You'd be surprised. Let's hear it from a student.
Hello, my name is Kari Armster, and I will be demonstrating for you a crushing can. But first I have to put on my safety glasses for safety. So in front of me is a can, some water with ice in it, and a pair of tongs. So right now I'm going to place this can of water, a little bit of water in it. I'm going to put on this hot plate. Well, after putting the can on the hot plate will warm the water up. Therefore, it will force out all the air that's in the can and fill it up with steam. Well, it looks like that I have enough steam coming out of the can. So therefore, see, the can crushed because there was no air inside the can, but there is air around us. So therefore, the air kind of pushes the can's particles together, and then it crushes up just like that. I'm Kari Armster, and thank you for watching my crush can demonstration.
Well, look at it this way. When the experiment was started, we had a little liquid water down at the bottom and air on top of that. When the liquid gets heated, it turns into a gas, and so much of it gets created, it forces out all of the air, so all you have left on the inside is steam. The can gets turned upside down into the cool water, and the steam cools down and turns back into liquid water. So what's left on the inside of the can?
Nothing.
That's right. All the gas in there is gone, so the pressure is very low, and the pressure on the outside of the can is very high, and that causes it to be crushed.
That's pretty awesome. You have a new way of crushing cans, using air pressure.
Yeah, it's going to take a while if we do it that way, but it's important for you to realize that all of the air molecules in our entire atmosphere adds up to a very high pressure.
I'm starting to get that.
Air pressure at sea level is about 14.7 pounds per square inch. That's like the weight of a bowling ball on every square inch of your body.
Wow, that's a lot. So I guess that we have more gas, we have more pressure.
Yeah, that's right. Now, do you want to see the exact same experiment again?
What do you mean?
Well, let's go over to UIC and see it done with a 65-gallon oil drum.